Now I'll do one more for today to introduce another useful way to treat constants. So here's a differential equation. It is now written in Lagrange notation instead of Leibniz notation. We're saying that y prime equals x squared y. Well, if we're going to do this multiply on both sides trick, then I really do need that Leibniz notation. So I will say that dy on dx is equal to x squared times y. This is one of the first places that we're seeing one of the notations being more useful than another. So if this equation is true, then it must be true that dy divided by y is equal to x squared dx, so long as y isn't 0. Once again, I'm going to integrate on both sides, and I find that the natural log of the absolute value of y is equal to x cubed on 3 plus a constant. Well, great, I can solve that for y. I just have to use an antiderivative. Excuse me, I just have to use an exponential. So the absolute value of y by itself is going to equal e to the power, the natural log of the absolute value of y. So I can substitute in and say that that's just e to the power x cubed plus 3, all plus a constant. Is that making sense so far? Just using my algebra, using my inverse functions. So y has to be equal to e to the power c times e to the power x cubed on 3. Now, since the absolute value of y is equal to all this stuff, y itself is going to be plus or minus that expression. Y is plus or minus e to the power c times e to the power x cubed on 3. Well, my independent variable here is the x cubed. Well, the x by itself, really. My dependent variable is y, and the c that I've got here is my constant of integration. So that is something that I would need to solve for, again, using an initial value problem. Now, what we're going to do is we're going to replace that e to the power c with a new constant. In this slide, we're calling it a. So I still have this idea that the constant of integration is just some fixed number that, for the time being, I don't know. Working with derivatives requires me to give up a certain amount of information, and I only get that information back when I have an extra condition to solve for. So maybe my constant is e to the power c. Maybe my constant is minus e to the power c, but those are still numbers that I'd have to solve for. So no matter what, I know that y is going to be equal to some multiple of e to the power x cubed divided by 3, which tells me that, well, I'm really just solving for y equals a times e to the power x cubed on 3. The short of it is that anytime we see e raised to a power that's a constant, we're going to be solving for that constant anyway, I might as well just call that a constant by itself.